Okay, so let's get started. So we're happy to have Zhenghao Zhong from Oxford. He's going to tell us about the Higgs branch arch flow and blah blah blah.
Thank you. Thank you for having me here in Shanghai, my hometown, best city in the world. And overruled. So today I'll be talking about a very recent paper in collaboration with Antoine Bourget and Marcus Berg. And this is based on a paper which just came out. The short version came out in December, and the long version came out 2 weeks ago. And it's about Higgs branch RG flows via decay and fission of magnetic quivers. So, now, what are the kind of theories that I'm talking about? I'm talking about supersymmetric gauge theories and superconformal field theories with 8 supercharges. And the space-time dimensions 3, 4, 5, and 6. So this gives us 3D equals 4, 4D equals 2, 5D equals 1, and 6D 1,0 theories. These are the only theories that I will be talking about. So we're dealing with quantum field theory with supersymmetry. So the quantum fields are neatly packed in supermultiplets. And because we have 8 supercharges, we have hypermultiplets containing some scalar fields and fermions, vector multiplets containing one gauge field, some scalar fields whose number depends on the dimension you're in, and some fermions. And I am only interested in the scalar fields of these theories. So if I'm only interested in the scalar fields, what can I know about it? Well, we can study the vacuum of the theory. To be more exact, the moduli space of vacuum. So because we have 8 supercharges, we're going to have a Higgs branch moduli space and a Coulomb branch moduli space. But for these theories over here, I'm actually, for today, I'm only interested in the Higgs branch of 3D n equals 4, 4D n equals 2, 5D n equals 1, and 6D 1,0. And all of them will make an appearance today. So, Higgs branch. When I talk about Higgs branch, what I really want is to know the Higgsings of the theory, aka Higgs branch RG flows, aka Higgs branch deformations, depending on your case. So what does Higgsing mean? Or to be more exact, Higgsing along the Higgs branch. So I give some VEV to the scalar fields in the hypermultiplets. And as a result, the gauge bosons in your field is going to be massive, and the gauge symmetry will be broken into its subgroup. So this is the usual Higgs mechanism that you're familiar with. Take electroweak theory. It has SU2 times U1 gauge symmetry, and after giving VEV to the scalar field, your Higgs boson, it breaks the symmetry to a U1. And that's exactly what I'm doing over here. The only difference is that I have many new scalar fields from many hypermultiplets, and the gauge symmetry is much more complicated. But the idea is the same. I'm taking one theory, I'm performing a Higgs mechanism, and I see what I end up with. Now, the Higgsing I'm only doing for today are along the Higgs branches. That's why I give VEV to scalar fields in the hypers. But I can also do Higgsing along the Coulomb branches by giving VEV to scalar fields in the vector multiplets. But that's not what I'm going to do today. Today, only the Higgs branch. And there's a reason for that, as you shall see. All right, so what's the goal? Given the supersymmetric theory with 8 supercharges in 3, 4, 5, or 6 dimension, which I label as T, I wish to find all daughter theories, T prime, that it can Higgs to. And for all these daughter theories, I want to find all the granddaughter theories, T double prime, etc., 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 until I reach a trivial theory. Let me make this statement a bit more precise. Actually, I just want minimal Higgsings. So what does it mean to have a minimal Higgsing? Well, let's say our theory T, it undergoes some Higgsing, turn on some VEV of scalar fields. It goes to T double prime. But if I turn some other VEV, and it first Higgs us to a theory T prime, then to T double prime, then the first Higgsing is not a minimum. because it can be broken into smaller steps. So what I want are just all the minimal Higgsings. Why? Because this gives a better way, a more structured way in seeing how one theory hits to another. And also, if I classify all the minimal Higgsings in a theory, it automatically gives all the non-minimal Higgsings as well. So this is the kind of diagram I'm looking for. Starting with the theory T, I do some minimal Higgsings. There's only two for this example, T1 prime and T2 prime, the daughter theories, which then hits to the granddaughter theories, etc., etc. They all put together in a beautiful little diagram, a phase diagram, and which sometimes is called a Higgsing tree, and sometimes we call it a Hasse diagram. And this is the kind of things that I want at the end of the day.
Sorry, so when the Higgs branch of the original series reported home, is this Hasse diagram you obtain from Higgsing exactly the same as the Hasse diagram for the reported home?
Exactly. Yes. For the case of nuclear orbits, this will be exactly the same as the Hasse diagram, the nuclear orbits of any algebra. All right. So let's take one example. SQCD3 theory. SU3 with 6 flavors. Now we've seen quiver diagrams a lot today. Just a recap. This is a quiver gauge theory. The circles represents the gauge symmetry in your theory, so SU3, and the flavors are represented by the squares. So we have hypermultiplets and vector multiplets transforming under various representations under the gauge groups and flavor groups in the symmetry, and all these representations are captured nicely by the diagram. So all in all, a quiver gauge theory or quiver diagram is just a very nice, concise way of encoding the group theoretic content and the matter and the field content of your Lagrangian. So a quiver diagram will be how I represent my supersymmetric theory with 8 supercharges. Okay, so the Higgs branch of SU3 with 6 flavors. So this is very old-fashioned. The Higgs branch can be studied by looking at the Lagrangian, then I find the F terms and D terms, I perform what's called a hypercadar quotient, voila, here's the Higgs branch of the theory. I won't go into detail, this is something that is known way before, since the 90s. And Higgsing of this theory. So the Higgsing of SU3 with 6 flavors is also known for a long time, because you can use some old methods which we label as group theoretic methods, and everything will work out just fine. How does that work? Well, roughly, you give me the Lagrangian of the theory, I know the gauge symmetries, I know the flavor symmetries, then I just see what are the different gauge bosons and scalar fields and how they transform under the gauge symmetry and flavor symmetry of the theory. And then I ask myself, okay, SU3, maybe it can be broken to an SU2, maybe it can be broken to a U1. Okay, I make this conjecture, then I see if it breaks to SU2, there's going to be some massive gauge fields. Let's look at the irreducible representations of these massive gauge fields, compare it with the scalar fields that they ate, and if all the irreps match us together, this is a Higgsing that's consistent. So SU3 with 6 flavors can be Higgs to SU2 with 4 flavors, and if things does not match up, this is an illegal Higgsing. For example, SU3 would never be, SU3 with 6 flavors would never be Higgs to a U1 gauge group for some flavors. So this is known doing some group theoretic methods. And this kind of diagram, the minimal Higgsing from SU3 with 6 to the daughter theory, SU2 with 4, and then doing another Higgsing to get a completely trivial theory, this is exactly the kind of diagram I want. This is the phase diagram for the Higgsings of this theory. So, okay, goal achieved. But then it seems quite simple, right? Give me the Lagrangian of the theory. I can always find the F terms and D terms. Perform the hypercadar quotients, there's the Higgs branch. Give me the Lagrangian of the theory. I know the gauge symmetries and the flavor symmetries. I use this group theoretic method, boom, there's the Higgsings of the theory. But then, what's new? What is interesting? Well, things are not always so simple. And that's because all these traditional methods, hypercadar quotients, to do Higgs branch, group theoretic methods to do Higgsings, they only work if I have a Lagrangian description of the theory. But as we've seen over many talks in in this week, that especially for superconformal field theories, you almost never have a Lagrangian description. If I never have a Lagrangian description, then these old 90s methods fails catastrophically, and we need something new. So as an example, 61,0 theories. If you go to the UV superconformal fixed points, there's tensionless strings that enhances the Higgs branch. And as a result, I no longer have a Lagrangian description for the guy. I cannot find the Higgs branch. I cannot do the Higgs. 5dn equals 1. Similar story. Everything is nice until you go to the UV superconformal fixed point. Then suddenly the massless instantaneous enhances the Higgs branch. I don't have a Lagrangian description. Don't know how to do hyperkähler quotient. Don't know how to use group theoretic methods. 4dn equals 2, there isn't that kind of new particles arising at the higher fixed points, but nevertheless, almost all 4dn equals 2 SCFTs found in the literature does not have a known Lagrangian description. Like people try really hard to find the Lagrangian descriptions for, say, the E6, 7, 8 Minahan non-transitive field. And these are extremely simple theories in the landscape of 4dn equals 2 SCFTs. So general class S theories or Argyros-Douglas theories, we don't know what the Lagrangian description. So we cannot use this old 90s method. 3D equals 4.
To be precise, I mean, it's probably in principle the E6, E7, E8 cannot have because they have no coupling constant. So there's no free series limit for this theory.
Right.
So,
But then there's a Moroshi Song story where they
yeah,
force the fixed
so
point
it
and kind of.
requires flow from n equals to 1.
So even for E6, even 7, E8, it's not. I don't even know if anyone tried to use those conjecture Lagrangian doing the flows to do some Higgsings and stuff. So yeah, it's not looking well for the old methods with any kind of 4dn equals 2.
Yeah, in that case, you have to worry about whether this Higgsing and the RG flow communicate with each other.
Oh, I see. Okay. Yeah, that's true. Okay, then. Some interesting work to be done there. 3dn equals 4. Most SCFTs people study kind of have a Lagrangian description in the sense that if I draw any quiver diagram, okay, not any, if I draw a random quiver diagram, odds are they will have an IR fixed point and make some SCFT. So in that case, where I do have a quiver diagram for 3dn equals 4 theories, sure, we can use the old methods to study them. But even for the cases where the old methods work, I would argue that the method I'm going to introduce today is far more efficient and superior than those 90s methods. So, one thing to realize about Higgs branches is that it's really a nice thing. Regardless of the dimension you're in, as long as you're dealing with H supercharges, the Higgs branch is always going to be a hyperkähler manifold. To be more exact, it's going to be a hyperkähler cone or union of hyperkähler cones. The Coulomb branch, on the other hand, changes drastically depending on the dimension. Hyperkähler manifold in 3D, some complex Kähler or rigid complex Kähler in 4D, real manifold in 5D doesn't really exist in 6D. But the Higgs branch, no, the Higgs branch is good. Higgs branch is something that is so universal regardless of the dimension you're in. So there should be a tool, a single tool, that works in studying the Higgs branch regardless in these dimensions. And that tool is called a magnetic quiver, as I shall introduce. So the magnetic quiver, of course, examples of it exist all the way in like 2010 and even before that. Recently it took on this name, and there have been a lot of progress in classifying and finding magnetic quivers, especially from audiences today, like Songsu, Toshi, and Yinan. So I will talk a bit about magnetic quivers. And the idea is that the magnetic quiver is, by definition, encodes everything about the Higgs branches of all of these theories, regardless of whether or not there is a Lagrangian description. So that's what makes it really powerful and also very universal. And once I have the magnetic quiver, then we go to the new topic, the new tool that we introduce, and it's called the decay and fission algorithm. So the idea is to use this algorithm, apply it to magnetic quivers, and this will perform Higgsings of all of these theories, even when you don't have a Lagrangian description. That is the main topic today. Okay, so first, definition of a magnetic quiver. So given your, for example, a superconformal field theory with 8 supercharges, the dimension can be 3, 4, 5, and 6, doesn't matter. The corresponding magnetic quiver is a 3D n equals 4 theory, such that the Higgs branch of this SCFT is the same as the Coulomb branch of this 3D n equals 4 magnetic quiver. So there's a few things to say here. First of all, why Coulomb branch of 3D n equals 4 theories? So we've seen just now from Wenbing's talk where there's a lot of interesting things when we talk about Coulomb branches of 3D n equals 4 theories. And this stems from the fact that in the last decade, there is so much progress in understanding the Coulomb branch of precisely 3D n equals 4 theories. We're turning something that is notoriously difficult to study into something that's really, really familiar with, like something that we're very comfortable with. So that's why, if we can take the Higgs branch of all of these, say, SCFTs that does not have a Lagrangian description, so I don't know how to tackle the Higgs branch directly, but if I can somehow translate it into a 3D n equals 4 magnetic quiver and study its Coulomb branch, then this really goes into our comfort zone, and we can apply all these tools we used in the last 10 years to study the Higgs branch of all these different SCFTs.
Yeah, sorry, another comment is I realized what I just wrote there is in your terminology, magnetic quiver of the 3D Gen 7 series.
Perfect. You see, that's why I put your slide. Excellent. And another comment is that this equivalence only makes sense if the magnetic quiver is 3D n equals 4. Because I said before, only in 3D is the Coulomb branch also a hyperkähler manifold. So if I wish to put an equivalence between the Higgs branches, which are always hyperkähler manifolds, with other hyperkähler manifolds, it only makes sense if I talk about Coulomb branch or specifically 3D n equals 4 theories.
So just a question.
Yes.
So is the magnetic quiver generically unique or not?
Is the magnetic quiver generically unique?
No.
That's a good question. The answer is no from this definition,
Yep.
but from the way magnetic quivers are derived,
So
it could be.
there's in practice some sort of standard way to create a magnetic quiver.
Yes, and that will be the next slide. Thank you. So how do we get to magnetic quivers?
Actually, another comment on that question is for a lot of Dirac-Douglas series actually have the same Higgs branch. Its 3D mirror quiver are differed by some decoupling.
Right, by some free hypers.
Free hypers.
Yeah, that's right.
Yeah, that's a sort of trivial example of the
Yeah.
different quivers.
Yeah, that's right. So I guess you can follow the diagram by either adding flavors explicitly, or sometimes if you add some adjoints to U ones, like in your papers, then yeah, it's can lift some of the degeneracies. So how do I get all these magnetic quivers, which I advertised so hard? Well, the usual way to do so is via a brane system. So the idea is, I take a brane system, I massage it a little bit so that the movement of the branes describes the Higgs branch of your theory. And then I take the branes, I move it a bit more so that it describes the Higgs branch, but also at the superconformal fixed point. Now I have a brane setup that describes the Higgs branch at a superconformal fixed point. Then I use some algorithms to extract the magnetic quivers from it. So for 60, the brane setups will be some type 2A brane setup with some D6, D8, and 5 branes with possible inclusion of oriental planes. 5D is going to be some bound states PQ5 branes ending on some PQ7 branes. 4D, we don't really have a nice brane system for it, but we do have some bottom-up constructions of quivers, and we also have some tricks called folding quivers. So with these tricks, we're actually super successful in finding magnetic quivers of 4D n equals 2 SCFTs, even extremely abstract ones that doesn't have a class S description. 3D, we have the usual stuffs. the Hanabi-Witten setup of D3, D5, and N-1. Okay, so once I have a ring system, I extract a magnetic quiver. I won't show you guys how I extracted magnetic quivers. It will be a whole different talk, but rest assured, it's doable. So let's use an example. Let's choose a 4D equals 2 SCFT. So by the way, I'm only talking about SCFTs from now on, but everything I say applies for theories even when they're away from the superconformal fixed point. It's just as when we talk about SCFTs, sometimes it's more interesting. So here's a very, very simple 4D equals 2 SCFT. Probably the second simplest SCFT in the whole landscape. SU3 with 6 flavors. So it's nice enough that it has a Lagrangian description, so we can do all sorts of calculations for it. So this example is just as a consistency check. Okay, so the magnetic quiver is given over here. And just as a refresher, this means that Higgs branch of this 4D equals 2 theory is the same as the Coulomb branch of this magnetic quiver, which is a 3D equals 4 theory. So all the gauge groups here are unitary, and for today's talk, all the gauge groups of magnetic quivers are always going to be unitary. So sometimes I just label by the rank of the gauge groups and don't write the U's. Cool. Okay. But what I really want is to do the Higgsing theory. So let's say I do a minimal Higgsing. I don't know what the answer is. Okay, we know what the answer is because we did this example previously. But let's say in general we don't know what the answer is. How do I find this answer? Well, minimal Higgsing. Higgsing is really just a movement along the Higgs branch from a more singular point of the Higgs branch to a less singular point. That's all there is to it. So if the magnetic quiver, by definition, contains all the information of the Higgs branch of this theory, then perhaps, well not perhaps, I should be able to do some manipulations on this magnetic quiver so that whatever is left describes the Higgs branch of the Higgs theory. That makes sense. And that's exactly what we found. So we use this decay and fission algorithm. In this case, it's kind of just the decay parts of the algorithm. And we obtain this 3D n equals 4 theory. And the idea is that the Coulomb branch of this 3D n equals 4 theory is the same as the Higgs branch of my Higgs theory, my daughter theory. That's the idea. So this is quite powerful because in general, if I have some SCFT, I'm telling you that as long as you can find me the magnetic quiver, I can tell you exactly how many daughter theories it can minimally Higgs to, how many granddaughter theories, etc., etc. And for each one of those Higgs theories, I can tell you everything about the Higgs branch because I have the magnetic quiver from this decay algorithm. Now, knowing everything about the Higgs branch of this theory is not really enough because the Higgs branch does not completely define your SCFT. But it's such a ridiculous amount of information that in practice, it can almost always allow you to match with the correct SCFT from the literature. So that's quite surprising and nice.
So in this example, why the minimal Higgsing corresponds to this particular decay?
Very good. So so I haven't introduced the algorithm or why it works yet.
Okay.
So after this slide, I'll introduce slide. Thank you.
So you're saying the correspondence is one to one?
The correspondence is
Between theory and the magnetic quiver?
not quite. But if you use some, so just by looking at the theory itself and try to apply some common sense depending on the quivers, it's actually very easy to lift pretty much all the degeneracy. Like for example, let's take the simplest moduli space, C2 mod Z2. So there's infinite number of theories whose Higgs branch is C2 mod Z2. But I can take, let's say, the U2 with 4 flavors, which will be an example later actually. I know that it hits us to U1 with 2 flavors. That's C2 mod Z2. But it's less likely that it's gonna hit to SU100 with 2 flavors, which is also C2 mod Z2. So actually this bits of common sense is surprisingly powerful in lifting a lot of these theories. Because normally what happens is when you Higgs a theory, it tends to stay within the same family of theories or some neighbors. So that's actually yeah. Okay. So, oops, spoiler. So the Coulomb branch of this, you can study it. You can either look at the diagram itself and instantly jump to a conclusion, or you can compute, say, the chiral ring of the Coulomb branch, and you'll tell me it's the one SO8 in some harmonic space, or minimal Newtonian orbit of SO8. So which 4D equals to SCFT has exactly this modular space as the Higgs branch? SU2 with 4 flavors. So from this, I conjecture with high confidence that SU3 with 6 flavors will be Higgs to SU2 with 4 flavors. I do the process again. It's going to decay to some trivial theory, which means the Higgs branch of the next Higgsing will be trivial. So in this case, I conjecture that this is actually a completely trivial theory and not just a Higgs branch. It's trivial. So this we can easily compare with the group theoretic method that we've just done, and everything matches perfectly. SU3 with 6 flavors, Higgs to SU2 with 4 flavors, which are Higgs to a trivial theory. So that's good. It's a consistency check and a sanity check. But of course, just looking at this simple example and the fact that I already know something about this because it's a Lagrangian theory may not convince everyone that this result works. So hopefully, later on, as I go through a plethora of examples, this will become a bit more convincing. Because there are other methods in performing Higgsing in the literature. They're usually very specific depending on the family. For example, consensus theories can be Higgs using this partial closing of functions. And I would just like to say that every single time that we're able to match with the Higgsing in the literature, regardless of the dimension they're in, it's 100% match in all these cases. And it all follows from the same decay and fission algorithm without any modification. Okay, and then now let me try to convince you why this algorithm makes a bit of sense.
I'm sorry, I'm a little bit confused. Is it necessary for you to consider only SCFTs?
No, not necessarily.
Yeah.
And in cases that are not SCFTs, normally you can use this group theoretic method, and then it all matches completely as well. And it's
Pardon?
yeah.
So it seems that what you the decay is like removing the balance node. But why is it related to the minimal fixing?
Very good. This is exactly the next part. And actually, it's not just a balance node in general. So, yes. Okay, I hope the next part will convince you. So, consider. Actually, you told me the answer. That's why I called the acceleration about this. So, consider U2 with 4 flavors. Now we jump from the 4D example to a 3D example. So this is a 3D and plus 4 flavors. So I can draw a diagram that tells me about the Higgs branch of U2 with 4 flavors. And this is the usual Hanami-Witten setup. You have D3 brings the horizontal lines, D5 brings the crosses, and the NS5 brings the straight lines. So, arranged in this format, the D3 branes can move along the D5 branes, which extends into the projector. Now, the position of D3 branes along D5 branes precisely give the VEF of the scalar fields in the hypermultiplets. And that, by definition, is how we parameterize the Higgs branch. So the various positions of the D3 branes along the D5 branes will give you the Higgs branch of the theory. So that's why we call this the brane setup when you put it in the Higgs space. And from the Higgs space, I do some algorithm and I read off the magnetic quiver. So I won't explain the full algorithm, but one part is the gauge groups come from dynamical branes in your brane setup. So in this brane setup, the D3 branes are the dynamical ones, the NS5 and D5s are non-dynamic. So the single D3 brane here, the U1 gauge group. The stack of 2 D3 branes, the U2 gauge group. D3 brane here, the U1 gauge group. And now I want to do a Higgsing. So to do a Higgsing, I take this D3 brane and then I move it to infinity. Because I want to give it some VEF, I Higgs it away. So then what happens in the magnetic quiver? Well, when I move it away, I only have one D3 break left. So this U2 becomes a U1 gauge group. And that's the result of Higgsing from the break setup. But I'm not done yet, because I actually just want the interactive field theory in the end. But this theory contains some free hypers inside. Well, technically free twisted hypers inside. So I want to get rid of them. So how do I use that? Well, I look at something called balance from Galto and Witten. So a balance of a gauge group is basically the number of edges it's connected to minus twice its rank. If the balance is greater or equal to 0, it's good. If it's minus 1, it's ugly. If it's smaller than minus 1, it's a bad gauge group. So this U1 has 2 edges from the hyper, one from this, one from this. That's 4 edges. The rank is 1, so 4 minus twice its rank give you 2. This is a good node. We don't touch it. U1 has 1 edge, minus twice its rank will give you minus 1. It's an ugly node. This other U1, also ugly. So if they're ugly, it's a sign that there's some free hypers inside. So I get rid of it by doing a set of Zyber dualities. And what's left is this theory over here. So this means the original theory, which is U2 with 4 flavors, it will Higgs to some theory whose Higgs branch is described by the Coulomb branch of this object. And for those that are familiar, the Coulomb branch of this is C2-C2, which is the same as the Higgs branch of this, which is kind of trivial because it's a self-dual theory. So that's the main idea. Now, okay, but actually I don't even need to look at the brane setup in general, right? Because all I'm doing is I'm taking one dynamical brane and I'm moving it to infinity. And that takes one of the gauge groups and reduces rank by 1. So maybe I just look at the quiver itself, select a random gauge group, reduce the rank by 1, see what happens. If the remaining gauge groups are all good, I stop. This is a resulting quiver whose Coulomb branch describes the Higgs branch of the dollar theory. If some of the remaining gauge groups are ugly, then I shake it a little bit to get rid of the free hypers, and whatever is left is a perfectly good quiver whose only good gauge nodes, whose Coulomb branch describes the Higgs branch of the dollar theory. If I reduce the rank by 1 and there's some gauge nodes that became bad, I stop immediately. That's not allowed Higgs from the beginning. So then I repeat this process on every single gauge group of the quiver, and then every time it hits us to a dollar theory, I repeat this entire process on each of the dollar theory's magnetic quiver and every single gauge group of those theories. Repeating this will give me the complete Higgs branch phase diagram of magnetic fields.
Sorry, cyber duality, what you mean is that that bigger theory flow to the same infrared fixed point as that theory plus free hypers. Is that what you mean?
So here, yeah, it's just so I say cyber duality. What I mean is just UN with NF flavors become UNF minus N with NF flavors. Yeah, that's just what I mean. And I think that's also how cyber duality works in 4D, so they have that name whenever I try to. Yeah.
I see. So you're saying that there are some rules in the 3D world that like cyber duality?
Yeah, it should be
that would allow you to get rid of the free hypers?
Exactly. That's how we do, yeah. So doing that on all the ugly nodes, you'll find out that in the end, however many ranks you get rid of, it will be h to the power of that, which will be the free hypers. Right. So the process I just said about doing this on every single gauge node to do the Higgsing is kind of an overkill, because not all the Higgsings done this way will be minimal. Some of them will be non-minimal Higgsings. And also it's quite a laborious process. But I already know the answer that I want to have. The answer is I want to find, when I reduce the rank, I want to find some sub-quiver that is good, where all the gauge node is good. So rather than doing this process of doing Zyber dualities, why don't I just find all the possible sub-quivers that are good given this quiver theory? This should be the same answer. And this is a lot more, well, just much simpler to do. And this is what the decay is. So given the magnetic quiver, I find all sub-quivers such that each of the gauge node is good. So let's find an example. This is a magnetic quiver where all the gauge groups are unitary of some theory, whatever. Okay, let's find all the subquivers. Of course, I'm not going to do it by hand. We have a computer for it. So, in fact, the Mathematica code to do everything I'm going to say today is already linked inside the paper. Extremely easy to use, extremely fast. And this, we find 8 subquivers. I label the gauge groups with rank 0 just to make things look nicer, but it's not necessary. So these are all subquivers that are good. 8 of them. Okay, that's easy to do with. And now look, something really cool happens. Yes! Took me 3 hours to do that animation. Now, and then you find how they're connected to each other. So, the lines means which subquiver is a subset of another. So this is a subquiver to this. These two theories are a subquiver to this, but of course they are not subquivers to each other. And this is just a way of saying I put a partial ordering to the different magnetic quivers. So if I put a partial ordering and put them in a diagram, this is also called a Hasse diagram. Cool. And here, actually, I want to make a cool analogy to actual physics. And that is, the red lines over here, we call them alpha decay. Because the dimension of modular space changes more than 1. Just like how in nuclear physics, alpha decay, the proton number changes more than 1. So that's beautiful. And we also have beta decay, which are the blue ones, where the proton number in nuclear physics change exactly by 1. And this actually has some mathematical indications.
So the beta decay changing the minus 1.
Yeah.
Sorry, not charge.
Yes. So exactly, it's a proton number. So, okay. There's some mathematical reason for this. Because even though I'm interested in the end results, the space in between is also important. So this is the transfer space of your theory before and after Higgs. Because after the Higgs, some of the scalar fields go bye-bye. They're just released. But when they get released, they actually also form some singular space, which is also hypercade. So it's important for mathematicians to verify what the transfer space is. So the blue lines are actually Kleinian singularity transfer spaces. The red lines are either closures of minimal orbits, orbitals of some free theories, or something more abstract. So there is some more intricacy of it. There's no gamma decay, sadly, because the dimension will always change.
So
Yes, please.
I'm just wondering whether in the study of symplectic manifolds, symplectic singularity, is it known that these are the only 2 possible quotients of symplectic leaves, or can there be more?
Yes. So this is in the dictionary of isolated symplectic singularities, and it is not fully classified in the literature. And I will show you in the end how. I just mentioned that this algorithm can actually help to identify new isolated symplectic singularities. Like, if I'm just doing decay, I don't care if I don't have a known isolated symplectic singularity. I just find the next good subquivers. But once I have these daughter theories, I can actually do another trick that will tell me exactly what space is in between in terms of 3 labels for unitary quivers. So that actually uses this algorithm as a way to identify new isolated symplectic singularities.
I see. So you are saying that you are going to tell us more about things besides Kleinian or Neapolitan orbits?
Yeah, Neapolitan orbits, Kleinian, orbitals of free theories, and more abstract ones, which I will show in the last slide.
Okay, thanks. So what if you get a bad theory in your subtraction?
Then you stop immediately.
Okay.
Yeah. That's why if I just find good subquivers, I'll never have a bad theory.
Okay.
This way. Thank you. Because the reason is because Higgs branches are always hyperkähler cones, but bad Coulomb branches are not hyperkähler cones. They have more than 1 singularities in the end. So I cannot choose in those theories. They will never be mapped to a Higgs branch.
Thanks.
It's interesting that here the number of alpha decays and beta decays are conserved independently. is it possible to just like using the ordering of alpha and beta and figure out correctly the possible Higgsing?
What is conserved here?
The number of alpha decays and beta decays. Because in each way of decaying to the final result, just like you have the same number of alpha. So it's like you have the number of steps is fixed, the number of alpha and beta are each fixed. So it's like combinational problem that you have some ordering some alpha and beta, and is there an easier way to like understand it from this one, not drawing all these diagrams explicitly?
So here the number of steps of alpha and beta reaching the end is the same as pure coincidence.
Okay.
But in general, that is an interesting question. If one can bootstrap this kind of idea just based on the kind of transitions that it can have consistently, that's actually one of the future outputs. Okay, cool. So let's map it back. This is a theory corresponding to some gauge theory of SCFT. And what this is telling me is that it first had one minimal Higgsing to T prime, whose Higgs branch is given by this theory. Then I have two minimal Higgsings, T1 double prime, T2 double prime. T1 double prime has a Higgs branch described by this, T2 double prime described by this, etc., etc., etc. So very beautiful. I tell you exactly how many Higgsings there are and the Higgs branch each one of them. Now, let's deal with fission. So, fission is something that is quite rare to see in the literature when you translate back to Higgsings, but extremely important because many Higgsings in the literature, they exactly miss this fission process. Okay, so a quiver can always be split into a product of two quivers, Cartesian products, as long as all the gauge groups of the resulting quivers are good and the gauge group's ranks are preserved. So for example, I start with this quiver, then at this position, the gauge group rank is G1, which means after I do this fission, the new gauge groups at this position is H1A, H1B, then better H1A plus H1B equals G1. So this is actually really constraining, which is why all the previous examples, we do not see any examples of fission at all. But in general, it does happen. In fact, it happens for very simple theories that looks like this. Okay, so let's do a fission. Back. This is all done just with PowerPoint. Proud of myself. Okay, this is fission. So this theory will be fission into a product of these two. So let's say it works. Okay, all the gauge terms are good, all the gauge terms are good. 0 plus 1 equals 1 over here. 1 plus 0 equals 1 over here. 1 plus 1 equals 2. Ranks are conserved. Valid fission. What does that mean? It means I start with the theory T, whose Higgs branch is described by this, and then there is some Higgsing that turns it into a Cartesian product of TA1 and TA prime and TB prime, where the Higgs branch of TA prime is described by this magnetic quiver and TB prime by this. So this is pretty cool, and actually it's not completely crazy, because there are certain Lagrangian theories, S2CD with some antisymmetric matter, where it can show explicitly using group theoretic method that you can break the theory into a product of two Higgs and Higgs. And what we find is that when you apply this fission rule to general SCFTs, it's almost ubiquitous, even in concept theories. It's just that many people, when you look at the literature, you look at smaller SCFTs, and then these never arises. But for more complicated ones, my God, it's everywhere, which is cool.
So just to make sure, so the rule is that as long as the daughter theories are all good, then this can happen.
And also, the ranks at the position is preserved. Yes, that's really the one that kills off a lot of possibilities. Okay, now let's get to good stuff. SCFT does not have a known Lagrangian description. Okay, this, maybe someone does, probably not, I don't know, but it's okay. So the magnetic quivers, well, okay, this SCFT is a 4D equals 2 SCFT, and it can be represented as a class S theory, which has a circle with regular punctures, where the numbers, partitions, label the ion tabloids of the regular punctures, which tells me about the pole structures of this. This is the usual process theory. It has been known since 2010 what the magnetic quiver is, although they call it that, of course. And this is from the paper of Banini, Tachikawa, Xie, and Banini, Tachikawa, Benavuti. So the magnetic quivers, they're always going up. They're always going to be what we call star-shaped quivers. So this is a star-shaped quiver. All the gauge groups are unitary. The black nodes are those that with balance greater than 0. The white nodes has balance equal to 0. Don't have to worry about that. So we do the decay, it's fine, you get this theory. In the end, this A3n is just a way to label the transfer space in between. So okay, this is the guys we want, and because everything is class S, I know how to immediately map these star-shaped quivers back into a class S theory. And this is mapped back to what's called a R0,4, 40n equals to SCFT. Nice and good. Do another decay, boom, boom. This maps back to the E6 Minahane-Lorentz. This maps back to the E7 Minahane-Lorentz. And then these fix to a trivial theory. So this fix to a trivial theory. In general, when I say trivial here, it doesn't mean the theory itself is completely trivial. It just means that the Higgs branch is trivial. And then you cannot do any Higgsings, of course. All right. Okay. So, as promised, non-Lagrangian theory, I don't have the group theoretic tools available to do the Higgsings. Doesn't matter. Use the magnetic quiver, use the decays, bam, map it back. Here's our SCFTs. Get Higgsings. Now, because these are class S theories with regular punctures, we can do a consistency check. So, there is this idea of partial closing of punctures that is known to correspond to Higgsings in class S. And this is a perfect example to do that. And we show that indeed, the partial closing of punctures, which is just moving ion tabloids, will give this Higgsing back. So everything matches perfectly. But even for class S theories, the partial closing of punctures does not give all possible Higgsings. There are ones that they miss. There are ones where they hit this class S theories, they be like, okay, the Higgs branch is not trivial, but I have no idea what to do next in terms of partial closure of punctures. And those examples that they cannot do is precisely the fission ones. And that occurs not in T4, but as soon as T6. So it's important that we have both fission and decay inside the algorithm. And this gives you every Higgsing for these SCFTs. We're not missing anything over here. So let's do something more exciting.
So,
yes.
fission, from the point of view of class I theory, corresponds to tuning the parameters associated with two punctures at once, or something like this.
So for the fissions, we just break this circle equals to 2, and then it'll be a Cartesian product of the two of them. So,
yeah, but I mean, from the point of view of Higgs branch parameters, I'm moving along some directions, right? And it seems that it has to be combination of direction coming from multiple punctures, right? It's some combination of those.
that is right. That is right. Yes, because when you split in terms of magnetic curve, when you split the star shape, you're changing everything in terms of all the different punctures and the algebra itself as well. Yes, that is right. All right, something more exciting. Algebra Douglas theories. So here is not really a good label of algebra Douglas theory, but here we go. Here's the label for the irregular part of the algebra Douglas theory. And here's the label for the regular part, which is just ion tabloids again. Because you can see Argyros Douglas theories again as a class S theory with one irregular puncture and one regular puncture, or more. But in this case, just one each. The magnetic quiver is known since a long time ago by Xie. And one interesting thing is that the irregular puncture will correspond to some complete graph in the magnetic quiver. The regular puncture is just a straight line. Okay, so let's do the Higgsings.
What's black and white? Sorry.
Oh, sorry, these are the balance of gauge groups, balance or overbalance. In the old algorithm, it plays this one. So if anyone heard other versions of this talk, I used to give a name inverted quiver subtraction. It is the same as decay. But because my supervisor just published 2 other papers with the name quiver subtraction telling completely different stuff, we realized that I'm not going to use the word quiver subtraction anymore to name any of my stuff. So, yeah, so that was important there, and here it doesn't really matter. So when doing the decay, well, I mean, okay, it matters, but don't really need it as an input. So, decay, 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 decay. What happens? Look at the long tail that corresponds to a regular puncture. They get shortened after the decays. That's exactly how you see partial closing of punctures, because it changes the young tabloid in a way that shortens the tail in the magnetic quiver. Okay, everything nice and consistent, but something crazy happens over here. This is the first point where I can do something else. I can do a decay that changes this complete graph from 3 U1s to 2 U1s. There's actually 3 equivalent ways to do that. I'm showing you one of them. And I get this theory. So I'm changing the complete graph, which corresponds to the irregular puncture. So this means that now, possibly for the first time in the literature, I'm not sure, that I am doing a Higgsing on the irregular punctures of the Argyros-Douglas theories. Now I cannot do this by partial closing of punctures, because I don't have a young tabloid for these irregular punctures. But in terms of magnetic quiver, doesn't matter. I have everything, it's just unitary gauge rules, and bam, after decay, one of the gauge rules pops out. This is the resulting theory, the irregular puncture changes. I have a new Argyros-Douglas.
This might be tested the other way, because your configuration is irregular singularity with flavor symmetry plus a regular singularity with flavor symmetry.
Right, right.
So there is always a duality frame which change the theory. Another dual description of the theory is with the irregular singularity without any flavor symmetry, but with a regular singularity such that the commutant of the remaining flavor symmetry of that singularity is this T point.
Okay.
So in that case, one can definitely check that in the dual description, I suppose it should be true that you have the decay or Higgsing step exactly the same as the.
Oh, that can be a really cool check.
Yes.
Okay, wait, yes, we should talk about it. Thank you.
Yeah, and by the way, you should embrace the dark side, not using this notation.
Yes. Yeah, this notation may not be the best. I'll adopt yours.
Yeah, embrace the dark side.
Now, what is this in that notation?
DGBK. This is notation for the Argyros-Douglas series.
Okay, sounds more complicated.
No, it's a very confusing notation. Not very straightforward. Yeah, sorry.
And just to make sure, so whenever this irregular puncture has some flavor symmetry, you can Higgs it, right? But normally you just get trivial theory. Maybe you're saying that this is a simple example where this is non-trivial. Is that what you're saying?
You mean before and after it's not a trivial theory?
Right, so I assume that there are simpler theory like A1, A3, where you can also do just Higgsing given by
That's
irregular
right.
puncture, but you just get trivial theory.
So, yes, you can take the simplest theory where you're going to have a log regular puncture. It's just a complete graph. And then you see, let's say, actually this example, here's the complete one. You're close enough, maybe you can see it. So you can see there's a very simple theory here. That's just a complete graph. It's get Higgs to a smaller complete graph, just irregular puncture. And then you have A1, A3, which is just 2 of them, and then that Higgs is 2. Nothing. Yes. So this is the whole thing. So it's really quite bizarre. Like this central line, this part is what you get if you only do partial closure of regular puncture. And then we have all this crazy stuff. And then the red ones actually corresponds to fission. So there's some Argyros-Douglas theories that will just fission into a product of 2 Argyros-Douglas theories. It's quite dope. Okay. But enough of Argyros-Douglas theory. Let's go to crazier 4D equals 2 SCFTs. So this is a theory that is classified by Argyros, Martoni, and others when they try to do this scan over all low-rank 4D equals 2 SCFTs. So it doesn't have a class S description. It's not Argyros-Douglas theory. It has a label called Q2A3, which is the flavor symmetry A3 and the rank A2. We have the magnetic quiver.
Sorry, what is the Coulomb branch of that theory?
The Coulomb branch of this theory.
The Coulomb branch operator, scaling dimension of Coulomb branch.
Oh, I don't remember. Sorry. But it's in their list of the.
I mean, I also have a classification of rank 2 series. I mean, only like 1 or 2 examples in Argyros paper miss our scan. So I I think this is not that one. I mean,
Yeah, this one is probably in your paper as well. Like this is the one that are common in both papers.
oh, okay, then it has a class S this one.
No, but there's a lot, even in rank 1 theory that doesn't have a class S.
No, so all our paper, all of them has an irregular distribution class S.
Ah, okay, so it's a class S in terms of just regular.
Okay.
Okay, it could be.
I mean,
yes.
don't say this to in front of them later, because
It's okay.
He's watching right now.
Oh. Okay. So we have the magnetic quiver. Everything works out very well. We do the decay. We get this step. Map it back because we have an encyclopedia with 40 equals to SCFTs and magnetic quivers. Easy to map back. It's a rank 1 40 equals to SCFT with an A3 normal symmetry. Do the next decay. Map it back to this D41, which is actually just SU2 for flavors. And that's it. Okay. For this bizarre theory, no problem. Takes it back. Do the next one. This is now a rank 3 for the equals to SCFT of the same family. Magnetic quiver over here. Do the decays, no problem. Higgsing fission happens over here. Map it back to the SCFT. We have this beautiful diagram. So even for a simple rank 3 for the equals to SCFT, the Higgsing is quite involved. Yeah, it was very easy, fun to reproduce this. Okay, and I'm done with 4D stuffs. Oh, by the way, here it said undocumented 4D equals to SCFT as a rank 3. Maybe it is documented in your paper release then. And yeah, we know all the things about the Higgs branch. Okay, 5D theories. Cool. Finally done with 4D theories. So 5D equals 1 theory, the low energy description, SU5, 1 Chen Simons level, 4 flavors, 2 antisymmetric. Now, just because I have a low energy description doesn't mean all the Higgsings is trivial. Because once I go to the UV superconformal fixed points, as you can see from Song-Su and Toshi's talk, there's going to be massless instantons that enhances the Higgs branch. And this opens up new possibilities in doing the Higgsings. So, the magnetic quiver of this theory is known. Okay, we do a decay to one of them, easily map it back. It's SU4, 1 Chen Simons level, 2 antisymmetric, 2 flavors. Other direction, we have a fission, SU3, 1 Chen Simons level, 6 flavors, times SU2, 4 flavors. Everything went very well. And then we just do the rest of it as well. Cool. Each one of them, very easy to map it back to the 5D equals 1 SCFTs. So it will be nice to compare this result with Song-Su's result of also how to do the Higgsing directly from gray webs for these theories. Here is just, you can't see anything, but just an example of how we have 17 infinite families of SQCD theories. That's UV completion of 5D equals 1 SCFT, and they beautifully are connected to each other non-trivially. Okay, this one is cut off a little bit. There's a very faint line that connects these parts with this as well. So this is cool. Have this nice, beautiful, big phase diagram that shows how these different SCFTs close to each other. All right, 61,0, no problem. These are theories created with -2 and -1 self-intersection curves. We know the magnetic quivers, Higgs it, map it back. Here's this Orbi instanton Higgsings. And we can even look at 60 theories that are not SCFTs. We have little string theories. So these are those theories that were explored by this paper over here, and which just came out like 4 months ago. And they show the magnetic quiver for each one of them. No problem, we have the magnetic quiver. We immediately put it in the algorithm, and then we map it back, and now we have the Higgsings of the little string theories. So exactly, anyone that puts out this dictionary, or anyone that puts out the magnetic quiver in the literature, the same day and night with some coffee in Starbucks, we can map it all the way back in and give you the Higgsing tree. So if anyone's interested.
This is all the just manipulation on the quiver.
Just the quiver, exactly. All the data I need are the ranks of the gauge groups and their relative positions, and hence the quiver itself. I don't need to do any in-depth computations of anything because this is an extremely large quiver. But just the structure of the quivers, this is very easy. And everything, every example that I've shown today can be done with our Mathematica code, and they're all generated with less than 1 second, even this one. Okay, so let me summarize some advantages of this. It's extremely easy to carry out. If you wish to do it by hand, we have an algorithm for hand in the paper. But of course, even though you have a beautifully simple algorithm, it's no match to extremely stupid Mathematica code, which is just so much faster. So we included that as well in the paper. And let's just say that most methods of Higgsing in the literature, they miss one or more following. Like group theoretic, it requires a one description. And other methods like this moment map Higgsings, it may not always provide minimal Higgsings, so you might miss something in between. And many Higgsings does not give more obscure Higgsings like fission, which as we've shown is very important if you want to have a full fixed diagram. And most theories, or most examples in literature are focused in a particular dimension or particular family of theories. But for us, it can work in 3, 4, 5, and 6 dimensions, as long as it has 8 supercharges and we have a magnetic quiver for it. And also we can even tell you about transfer space geometry before and after Higgsing, which is important to understand the geometry of the theory. So that's one example. We can find these elementary transitions that you mentioned earlier, and we can identify arbitrary transfer spaces between not just one theory and its daughter theory, but one, let's say, the daughter theory and the great-great-great-great-granddaughter theory. We can understand the transfer space between these two theories, and this utilizes another algorithm the authors of this paper and 4 others came up with in 2019 called quiver subtraction. So for those that knows this 2019 algorithm of quiver subtraction, I just want to say that is completely different from our algorithm. We give very different things. One important thing is that our algorithm, today's algorithm, actually tells you about the Higgs branch of all the daughter and granddaughter theories, etc. This is not an information that is given in the 2019 algorithm. There are some intersections, some similarities between the two algorithms, and whenever that occurs, our algorithm today is much more efficient, simple, and superior. And by the way, just to say, we are also on the other paper, so we're not just attacking. Yeah, and here are all the isolated symplectic singularity we can easily discover using our algorithm. This is restricted to 2 or 3 nodes, and this is a complete set. The red one here is a new isolated symplectic singularity. It's crazy. It has like non-symplectic edge and then non-symplectic edge. It's insane. Okay, some future directions. One is with this very simple algorithm, we can try to find flows between seemingly very different families of SCFTs. So what I've seen so far is that they tend to stay in their own neighborhood. Class S theory sticks to class S theories, Argyros-Douglas sticks to Argyros-Douglas. But perhaps in more complicated examples, we can even see Argyros-Douglas theory that sticks to a class S theory which is only regular functors. I don't know if that's possible, but something like that is interesting to explore. We can also find missing SCFTs. So for example, in the journey of classifying all possible 4D equals 2 SCFTs up to a specific rank, now we can test, say you classify rank 1, rank 2 SCFTs. Now we can take one rank 2 4D equals 2 SCFT, find this magnetic quiver, and perform this Higgsing. If there's a daughter or granddaughter theory whose Higgs branch is not identified in a classification, then that could be something new. So this can help just double check everything works out. Also, we can maybe bootstrap new SCFTs by reversing this process and do unhiggsing. So Higgsing, we reduce the rank of the gauge groups so it becomes smaller and smaller. Unhiggsing, we increase them so it becomes bigger and bigger. Of course, this is easier said than done. It should be done systematically and assessed so that it might work. Another thing is there's these maximization theorems that argue under any RG flows, like A or C would decrease, and this F maximization says that free energy will decrease, and now we can use this algorithm to test whether or not this is true for more obscure kind of Higgsings like fissions, etc. It probably will be true, but it's still nice to test. And that's it. Thank you very much.
Questions?
So if you find some missing SCFTs, how do you identify them?
Sorry,
So So if you find some missing SCFTs from the magnetic quiver, so you know the magnetic quiver description. How do you know what is the SCFT on the other side?
Very good. I don't know, but I know everything about the Higgs branch of this missing SCFTs and what theories will Higgs to. So normally, I mean, in the literature, when you identify a new SCFT, you give flavor symmetry, some dimensions of the moduli space. It's always some partial information. And now I can give you everything about the Higgs branch, and hopefully some other brilliant people around the world can identify that as. For example, if I find a G2 theory after Higgs in a rank 2 theory, now that is a hint that maybe there's a rank 1 theory that has a G2 flavor symmetry, which is not something that is it's not in the identifications. Thank you.
So there are theories without magnetic quivers, right? So and then probably this algorithm will not be able to enable to identify all missing SFTs, given that we will stay at
No, wait, what do you mean theories that doesn't have magnetic quivers?
well.
You mean we haven't found it, or it shouldn't exist?
Well, most theories should not have magnetic quivers, right?
But if it doesn't have magnetic quivers, by definition, you wouldn't have a Higgs branch either. So then the Higgs
Why
envelope is
not?
terminated.
So it's just not a Lagrangian in the magnetic sense. Just like theories, there are theories that are non-Lagrangian in the electric sense. There
So
are also
you-
theories that are non-Lagrangian in the magnetic sense, right?
Ah, so you mean maybe there's some moduli spaces that cannot be described by a 3D n equals 4 quiver
Right.
H theory?
So it's not Coulomb branch of a quiver gauge theory, right?
Well, that's maybe, but that's yet to be tested. Like all these extreme isolated syncretic singularity, mathematicians just fiddle with them, and then we found exact matches to them. So it might be, but it's not clear to me that all theories cannot be described by 3D n equals 4 quiver gauge theories. And all moduli spaces, no, sorry, all hyperkähler cones or union of hyperkähler cones cannot be described by 3D n equals 4 quiver gauge theories. It may not be unitary. If it's orthosymplectic, actually this algorithm doesn't work. We need something new, and that's when it's clear.
Any other questions? If not, let's thank the gentleman.
Yes.